Yeah, thank you. I knew that. I pushed the button. So then I'm going to share the screen. And so here's where we left off in chapter 6. And so you can think of this chapter as having a couple of skills. One of the skills is being able to complete nuclear reactions. And so maybe I should have set up my iPad. I haven't used it yet. And anyway, so I have an iPad. I set it up with so I can use it on the whiteboard, but it's not on right now. But anyway, here's what the skill is. This arrow has to be treated as the equal sign. That means that the number of uraniums has to equal, the number of protons on this side has to equal the number of protons on this side. The number of things in the nucleus has to equal the number of things of the nucleus on this side. So the symbols don't have to add up because the symbols will be different on both sides, right? That's not the case for a chemical reaction, but that is the case for a nuclear reaction. So what if I was giving you this right here, and I didn't give you this? I gave you this, but I didn't give you this. How would I find out what's missing over here? Well, 92 has to be equal to 2 plus something. Well, that something has to be 90. So then I go to the periodic table, and what is the element with 90 protons? Well, it's going to be thorium, right? So now I know that this is 90. I know that this is thorium. Now I have to get the mass numbers to work out. So 238 is equal to 4 plus 234. So now that I've completed this, I can see what's going on here. Here's uranium-238. That's then how we call the isotope, right? It's giving off alpha radiation because this is the alpha particle. And what's left is thorium. So uranium-238 has transformed into thorium-234. So this is a nuclear reaction because it happened to change the nucleus. So if I would have a whiteboard to write on, or if I really started to use this iPad seriously, I could show you that I could leave out all kinds of different things over here, and you can still figure out what's missing because of the law of conservation of mass, and you'll have the periodic table. So you'll see that every entry into these nuclear equations has 3 pieces of information. It has the atomic number, which is the number of protons. It has the mass number as protons plus neutrons, and it has the symbol.
Mr. Davis?
Yeah.
What was the difference between nuclear reactions and chemical reactions?
A chemical reaction, you will not see one element turned into another element. Because what identifies one element from another is the number of protons, which is in the nucleus. So if that changes, it's a nuclear reaction. Chemical reactions are only about electrons, and the nucleus does not change.
Okay, that makes sense.
Mm-hmm. So here's strontium-90. So what if I left out this part right here? Okay. So that means that I have to have 38, which one I leave out? This one, right? I have to have 38 protons. So look at the charge on here. We treat the charge on the electron mathematically. So 38 has to equal -1 plus something. That would be 39. So 39 plus a -1 gives you 38. Well, what element is 39? Well, the periodic table would say that's yttrium. Then 90 has to equal 0 plus, well, that would be 90. So here we see that strontium-90 gave off beta radiation. When it did that, it transformed into yttrium-90. So this electron did not come from outside the nucleus. It came from within the nucleus. It comes flying out of the nucleus at about 90% the speed of light. And you see we had 38 protons, and now we have 39 protons. How the heck did that happen? So here's what happened. A neutron decayed into a proton and into the electron. That proton stayed in the nucleus. That's why this number went up. And that electron came flying out of the nucleus. And that's beta radiation.
Excuse me, Professor.
Yes.
You said the electron came flying out of the nucleus?
Yep.
But I thought the electrons are outside of, they circle the shell. They circle the nucleus. They're not found within.
If you lose an electron from there, that's simply a chemical reaction.
Right.
But this came from in the nucleus, where a neutron decomposed into a proton and into an electron.
So from a nucleus
stayed there, but the electron came flying out at about
So it's
90%
like
of the speed of light.
it's a product of that neutron?
Yes, it is.
I see.
So you can make a neutron, or a neutron can decompose.
Okay, thank you.
And this happens spontaneously. So by the way, all these periodic tables are a little bit different. It's interesting how when they made the bigger version of the periodic table, they didn't make this part bigger. So what I will tell you is that most of the information I get to write these nuclear equations came from right here. Okay. You see that? It's very difficult to read, even if you have it in front of your face. It's the table of selective radioactive isotopes. So now if I look on here for strontium-90, which I have to take my glasses off to do. Where is strontium-90 on here? Okay, there it is. You can see in parentheses it has 28.8 years. That's called the half-life. And what does it give off? It gives off radiation in forms of the beta particle. So that's where I get this information, although there's way more stuff than what's listed on the periodic table. I'm just making reference to that now for your enjoyment later.
So the reason why it's called strontium-90 is because there is extra neutrons, right? Because typically it wouldn't be 90. That's why it's an isotope, right?
Well, an isotope might be strontium-89. But strontium-89 would still have 38 protons, right?
Right.
So here's another one where cobalt-60 gives off beta radiation, gets converted into nickel-60, and you can see everything is going to add up there, right? 27 is equal to a -1 plus a 28, and then 60 was a 0 plus a 60. So that's similar to what we did up here. But what if I added something over here? What if this was missing right here? Well, then that would have to be a 0. And over here, this would all have to be a 0 as well. What is the entity that has absolutely no mass? It's simply gamma radiation. Okay, so that gamma could have been left out. It could have not even put there. Matter of fact, if you look at table of selected radioactive isotopes on the periodic table, in no cases do they ever mention gamma radiation. Anyway, I looked up this reaction, and this is what I found. If you had 100 grams of cobalt-60 and it decayed by giving off this beta radiation and gamma radiation, generally it would lose about 0.005 grams of mass. This is a tiny speck. If I told you, look, in the test tube, here's 0.005 grams, you wouldn't even be able to find it, maybe with a magnifying glass. If I take that 0.005 grams and I put it into E equals mc squared to convert it into energy, here's the math I did. Okay, so here's the speed of light squared. Here's the grouping of units right here. That grouping of units is equivalent to the joule. Then I converted it into calories because you're more used to seeing calories. Look at the number right there. That is a huge number. That number is equivalent to 200 pounds of TNT. So yeah, there's tremendous amounts of energy involved in nuclear reactions. So here's another use of gamma radiation. This is actually very important in radiation therapy. So we take cobalt-60 and we irradiate it with X-rays. And then you get what's called a metastable nucleus. And so you can indicate that by putting the M there, or some people use an asterisk up there. What that means is that the nucleus in cobalt-60 is no longer stable. So eventually it has to give off energy, and that energy is given off in the form of gamma radiation. So here's why this is important. You can go to the dentist's office, for example, and he's got a machine in there that can produce X-rays. So you can produce X-rays with normal voltage in a house or building. You cannot produce gamma rays. So how do we produce gamma rays for the use of radiation therapy and other things? Well, you take cobalt-60 and you simply bombard it with X-rays. And as you're doing that, the nucleus gets a little bit out of stability, a little bit torqued the other way, till eventually it cannot handle it anymore and it just collapses back into a stable nucleus, and it gives off that excess energy in the form of gamma radiation. So, what is antimatter? So antimatter is the mirror image of normal matter. Electrons are regular matter. The antimatter component of an electron is called a positron. It has the same mass, but it has an opposite charge. So anyway, we really don't know why there's not as much antimatter as there is matter in the universe. There's just a lot of things that we don't know. But what I wanted to do is show you another way of which equals mc squared can happen. It's called annihilation. So here's an electron, which is matter. Here's a proton, which is antimatter. Now, look at the charges. Are they going to be attracted to each other? The answer is yes. And what did we learn about Coulomb's law? So they're this far apart, they have a certain attraction. You move them closer, what happens to the attractive force? It increases dramatically. So essentially, the electron and the proton accelerate into each other, and when they collide, that mass is converted into energy by E equals mc squared. And the result is you get two gamma rays come shooting out in opposite directions. So that's another example of how matter and antimatter annihilate one another and get turned into energy. So I didn't put the year here. I wish I did. A couple of years ago, NASA has this satellite called the Fermi Gamma Ray Observatory. And so it's pointed into space. And the idea is to look at where are gamma rays coming from in the universe. You know, gamma ray spectroscopy, gamma ray astronomy. So every so often, somebody started noticing, what the heck? We just got a gamma ray that came from Earth. So immediately they're thinking, oh, it's the Russians or the Chinese or, you know, North Koreans or something doing something strange. But then when they started paying attention to it, what they found is that every time they got a gamma ray that was coming from Earth, there was lightning storms happening below the satellite. So now they believe that lightning creates these huge electric fields that accelerate electrons towards the speed of light. They smash into air atoms, creating both electrons and positrons. And then when the positrons and electrons annihilate one another, it gives off gamma rays. So here's something interesting. Every time you see lightning, you should really be thinking, oh my God, look, there's antimatter being created and destroyed. So what is lightning? So it basically happens when ice crystals up in the atmosphere start to rub against each other, creating static electricity. And so you have this electrical field of electrons that can flow between clouds. And if the charge gets large enough, it can basically zap and jump through the air into the ground. So why would that happen? Go back to what we were talking about, the difference between metals and nonmetals. Nonmetals, such as all the molecules that make up air, are insulators. So air is an insulator. What about the metals? The metals in the earth, they're conductors. So if the charge gets great enough, it will jump through the air trying to get to the metals in the ground. So essentially, we have the planet acting like a huge capacitor. So lightning bolt is only about 1/2 inch diameter, but it's about 5 times hotter than the surface of the sun. So lightning is when this thing goes through the air and rapidly heats up the air, causing it to expand. And then when it goes back, it makes that sound, right? That's the shock wave. So anyway, the last death from lightning strike in Hawaii was in 1959. It kills about 10% of the people that's hit by it. Your chance of being hit over an 80-year lifetime is about 1 in 13,000. But really, that's kind of a lot of people to get hit by lightning. I've seen talk shows where they got these people that come on the talk show and they've been hit by lightning 2 and 3 times. And I'm thinking, well, what are they, golfers? Think about this. If you're out golfing in a lightning storm, you hit the ball and now your metal rod is pointing up into the air. Probably not the safest thing to do. So yes.
Do they ever have like lifelong? Are they maimed permanently from the lightning?
Many of them are, but some seem to be fine. Yeah.
That is crazy.
I know.
3 times. Unbelievable.
I know. So the other way that we saw about converting matter and energy is, remember, nuclear binding energy, right? The previous chapter. So I gave a bunch of practice within this chapter here. So here's some things to think about. The subatomic particles are always the same. So I don't want you to get creative here and start making up your own. An alpha particle is always this. It's never this. Okay? Here's an electron. Here's a proton. Here's a neutron. Here's gamma radiation. Here's a hydrogen. Okay? So don't invent your own. I mean, I don't mean to stifle your creativity, but if you want to do creative things, then take an art class. What we're doing here is trying to figure out what the world is really doing, what it's really made up, how it interacts. We're looking for the truth here. If you want to invent your own truth, then take a political science class or, something like that. So the mass number is the number of nucleons in the isotope. It is not the number on the periodic table. Remember that? The number on the periodic table represents the average atomic mass for all the isotopes on planet Earth. All these are for one particular isotope. And then every entry needs at least 3 things: symbol, atomic number, and the mass number. So the answers to all of these are somewhere in the chapter. Notice that many times I gave very limited number of information, but I gave you a step-by-step way to figure out all the information. You don't have to follow it that way. You could start here, or you could start here, or you could start here, right? But the answers to all these are somewhere in the chapter. Then, what kind of nuclear reactions are possible? And this is where
You retarded. Don't touch me. Get up, no.
this is where I think I've made a contribution potentially to science, because I'm looking at Wikipedia, I'm looking at all the textbooks, I'm looking at all the stuff I had to learn, and you know what? It's just all over the place. So really, I was trying to figure out what is the best way to categorize nuclear reactions, and I think this works really well. So here's a concept that applies to most nuclear reactions. Any nuclear event that happens spontaneously will obey the concept of half-life. So as we go through these, I'm going to ask you if it's a spontaneous process or whether it's a man-made process. Okay. So here's the difference. If you were to have a bullet just sitting on the table, then all of a sudden, with nobody around, that bullet just blew up and went off, that would be spontaneous. If you took that bullet and you put it in a gun, and the gun was just sitting there on the table, and nobody is around, and all of a sudden it just blew up, that would be spontaneous. But if somebody goes over there and pulls the trigger, that's not spontaneous anymore. That's a man-made event. So the first category is radiation. So radiation is the spontaneous emission of energy or any particle equal to or smaller than the alpha particle. And the half-life principle applies because it's spontaneous. So here's an example. Positron emission is a form of radiation. So here's a carbon-11, is sitting there minding its own business. Then all of a sudden, spontaneously, a positron comes flying out of the nucleus. Okay, so what happens then? So notice that I have to obey mathematics. 6 is equal to 5 plus a 1. 11 is equal to 11 plus 0. Oh, so therefore that has to be the positron. There's no other choice for it to be. So positron emission is often observed as gamma emission because the positron will immediately collide with an electron and annihilate it. Okay. Anyway, positron emission, if you were to go and look at this table of selected radioactive isotopes, I can't see it right now. Maybe if I go up like this. Okay, now I can see it. Okay, you'll find several places there where you see positron emission happening. Okay, what did I do now?
So is the positron the same as a proton?
No. A proton is just a proton, and that's different than a positron. A positron is antimatter. It has the same mass as an electron. Okay, there we go.
Is it, I have here written in my notes, positively charged electron is a positron. Is that,
Yes.
is that correct?
Yep, exactly.
But how can an electron be positively charged? Because I thought electrons are negatively charged.
Yeah, but we're talking about not matter, but antimatter,
Yes,
right?
yes.
You don't encounter antimatter every day because it gets annihilated here on the conditions of Earth right away. At some point during the Big Bang, they were in equal amounts. But after the Big Bang happened, when everything started to separate out, then we started losing all the antimatter.
I see.
Do you mind just real quick explaining what antimatter is?
Antimatter is the mirror image of matter. So a positron, excuse me, not a positron, what am I trying to say? A proton, for example. A proton is a +1 charge, has a certain mass, about 1 AMU. So what would be an antiproton? Same mass, about 1 AMU, but it would have a negative charge instead of a positive charge.
It's like the opposite.
Yep, it's the mirror image.
But why is it called antimatter?
Because it destroys matter.
Oh,
Matter destroys it.
oh, interesting. Okay.
Yeah. Okay, so another type is fission. It's the spontaneous splitting into smaller nuclei. So here, the half-life principle applies because I just told you it was spontaneous. So here, uranium-236 gives off 3 neutrons, and at the same time, it breaks down into 2 smaller isotopes, right? So here's the problem with when people try to categorize nuclear events. Most of the time, they're a combination of these things I'm talking about. So what is fission? It's when a larger thing breaks down into smaller things. It just so happens this event also causes the emission of neutrons, neutron radiation. And the next one is bombardment. This is when an isotope is hit by another particle or energy. This often causes fission. It is not spontaneous. It's induced by man, so you cannot use the half-life principle. So here I'm looking at this event right here. Notice that the difference between this and all the other ones is that there's two things on the reactant side. So the interpretation here would be, here's an aluminum-27 isotope just sitting there minding its own business. Somebody comes along and slams it with a neutron. That's bombardment. Also known as neutron capture because it didn't do anything yet, just captured it. It's also known as neutron bombardment. But what we're going to say is this is, oh, this is in the category of bombardment. Now look at this next one over here. Here I'm linking two reactions together. Bombardment that produces radiation. So here is the first event, happens to be neutron capture. But what happens is now aluminum-28 is less stable. So what happens is it spontaneously gives off beta radiation. So notice 13 is equal to 14 plus a -1, right? So my point being here is I could show you this as a sequence, and it looks like neutron capture and then spontaneous radiation. Or what if I left out this intermediate part right here? Then you would observe that is bombardment causing radiation. See what I'm getting at? So your job is simply to say, oh, is it bombardment? Whatever it is you're looking at, it's going to be one of these 6 categories. It could be a combination of them. All you're trying to do is describe what's happening. Here's another one. So here's bombardment. So is this a spontaneous event? No, because there's two things smashing into each other. And yeah, for a fraction of a second, there may be neutron capture, but what happens is that uranium-235 goes through a fission and gives off neutron radiation. Now, this particular reaction is what happens in the atomic bomb. It's what happens in fission reactors. We do not have active fusion reactors in production right now, only fission. So let me see, I need to find this figure here. It gets pretty tricky sharing screens now because I'm going to have to change. I don't know how much control I have over this while I'm doing this. Now, how can I do that? So here is the nuclear chain reaction that happens in the atomic bomb. So here is uranium-235 sitting there minding its own business. So is uranium-235 radioactive? Yes, it is. If you look at this part of the periodic table again, here's what you'll read about uranium-235. Uranium-235 has a half-life of 7 × 10⁸ years. What? That means it's 0.7 billion years. That's a really long time, isn't it? So nobody's going to make a bomb and have to wait 0.7 billion years for it to happen. So you have a huge unstable nucleus, you trigger the reaction by hitting it with a neutron. This is a non-spontaneous event. So then it goes through fission, gives off, splits into krypton-92, barium-141. At the same time, it gives off 3 neutrons. But what do those neutrons do? They hit other atoms of uranium-235, causing them to go through fission. Now you got neutrons flying all over the place. And this is the reason why it's a chain reaction, a nuclear chain reaction. Because the neutrons are going to hit other uranium-235 atoms and cause them to go through fusion. Now here's a question. What if I had a bunch of other atoms in this sample, and those other atoms would simply be blocking the neutrons, preventing them from hitting uranium-235? Would it be a chain reaction? Would the reaction keep going? And the answer is no. So this is the reason why you have to purify uranium-235 away from all the other atoms that you can. Even if you have pure uranium from planet Earth, which you can mine on planet Earth, because that's the last element that you can actually find on planet Earth. All the bigger ones don't exist. You have to make them. Uranium-235 is the only one that really undergoes significant fission. So you also have to purify away the other isotopes of uranium. Pure uranium won't do this chain reaction. Does that make sense to you?
So you have to bombard it with a neutron in order for the reaction to occur.
Yeah, right. So it's a non-spontaneous event.
On the daily, do we bombard like other elements? Like, like what, how do you bombard an element? Like do we do that in our daily lives? Like, on the normal? Like
I certainly hope you don't. It takes very sophisticated equipment to do this.
Okay. Gotcha. Okay.
So anyway, you've probably heard the term critical mass. Well, that's a really bad name. It should be critical concentration. So you can imagine if those uraniums are all far apart, the neutrons are going to miss them. So that means that these uranium-235 isotopes have to be close together. And we'll talk about this a little bit later. But what does a bomb do? A bomb does not implode and make atoms closer together. It explodes and makes them farther apart. So you can imagine the technology we have to deal with here. An explosion would be the very thing that would undo a nuclear chain reaction. So to make a bomb, you have to first turn that into an implosion to get the critical concentration. So only about 0.7% of uranium, pure uranium, is 235. And the other isotopes have to be removed by enrichment. So this is the reason why we don't really have to worry about rogue nations having the technology to make nuclear weapons. It is simply a near impossible thing to do. But do we worry about it? Of course. So later on, it was found that uranium-238 can be converted into plutonium. Now, plutonium doesn't exist on planet Earth. So plutonium was first created in 1941. This is how they did that. So uranium-238 was hit by a neutron. So you have neutron capture. And then spontaneously, this is bombardment, and then spontaneously, it gave off a beta particle and turned into plutonium after giving off another one. So if you look at the overall reaction here, you have uranium-238. Oh, I see I have a typo there. I'll fix that as we speak because I can do that here. Uranium-238 turned into plutonium-239 and gave off two positrons. Excuse me. I still got to fix that because 238 does not equal to 239, so I got to figure that out. Okay. Oh. Okay, see, now I know why it was 239. I did this right here. I started from the green. Yeah, okay. That makes sense now. Sorry. This is what you go through when you write your own stuff. So then plutonium-39 can also be used to make atomic bombs because it can also undergo fission. It also decays into uranium-235. So if you look at the periodic table, there's an interesting element, number 43. 43 is in hollow letters. That means that it was a man-made element. They could not find it. There was a missing hole in the periodic table. They knew how many protons it should have. They knew the approximate properties it should have, but they couldn't find any on planet Earth. So in 1937, they were able to synthesize it. They took molybdenum-96 and they bombarded it with a heavy isotope of hydrogen. That's deuterium ion. Okay. So they had created a device called a cyclotron. And what the cyclotron did is it created, it created a way to accelerate a deuteron, which was synthesized chemically, but the cyclotron could actually take this charged particle and accelerate it and then smash it into things. A particle accelerator, right? So here's the deuteron. They used the cyclotron to smash it into molybdenum-96, that's bombardment. And what happened? It turned into technetium-97 and gave off neutron radiation. Does that make sense? Of course it doesn't. This is not the kind of stuff that you see in your everyday life, is it?
Not at all.
Humans don't do this stuff. Humans also don't make fantastic and wonderful creations to study neutrinos and black holes and stuff like that. It's just amazing what man has done. Most people, they don't care. They live their lives. It's like, oh, I got to go to Costco. That's where their heads are at, right? So here's the creation of element 115. So element 115 has been given names. The periodic tables that I have here, it hasn't put the names there yet. And so un pentium simply means 115. So here's what they did in 2004. They took americium-243. Oh, wait, but americium-243 did not exist. That's a man-made element. So they took one man-made element, slammed it with a calcium bombardment, there was a capture, and then it broke down into element 115, and at the same time gave off 3 neutrons. Okay. So this part of the reaction is bombardment. This part of the reaction is radiation. Does that make sense? This part is not spontaneous. This part is spontaneous. So of the isotopes of 115 that they wrote to make, the one that is the longest lasting, its half-life is only 0.2 seconds. You know, you wonder why people do this stuff, right? Yeah, it's an interesting thing. Why do people do this kind of nuclear chemistry? Well, why do people climb mountains? Why do people try to surf the biggest waves? Why do people do these things? It's human endeavor. Okay. So here's another one called electron capture. Electron capture happens when a proton captures an electron out of its orbit. So here's what I'm going to do to always make sure we know what we're talking about. Here's the example. Here's potassium 40. Is this a bombardment? The answer is yes. It's a form of bombardment because it's on both sides. I mean, you got 2 things on the same side. But I put the word orbital there to try to make you realize that this is not somebody coming along and hitting potassium 40 with an electron. This is an electron that was already in the atom. So it's closest to the nucleus. And is it going to be attracted to the nucleus? Yes. If it slows down enough and actually falls into the nucleus, it will combine with a proton and convert that into a neutron. That's exactly what's happening right here. Okay. So we go 19 plus -1 gives me 18. See, I get a transformation there, right? So to distinguish this from bombardment, I will always put the word orbital there. That's not done in the literature of the internet and stuff like that.
Wait, so how is it considered? I thought a bombardment was when it was man done, you know?
Right.
But
so
if,
I'm telling you, this is not man-made.
right,
If I didn't put the word orbital there,
it would
it
be
would look like it was man-made, right?
Yeah.
But I put the word orbital there because that's where the electron came from. It came within that same atom, so it's not bombardment.
So isn't that considered spontaneous?
Yes,
Okay.
spontaneous. Yep.
But it's just on the left side of the equation.
Yep. So if you look on this table of selective nuclear events, whatever it is, right, you will see EC in several places. That stands for electron capture.
So just to be clear, it's not bombardment.
Not bombardment. Right.
Spontaneous.
And in order to distinguish between bombardment and spontaneous is whether or not orbital is written.
Yes. Yep.
But how else? I mean, if orbital wasn't written, how would I be able to tell if something is bombardment or not, or spontaneous?
Well, you wouldn't unless you were a nuclear expert.
Okay,
Okay.
makes sense.
So if you go and you start searching the internet for stuff, you're going to get pretty confused with this.
Right, right.
Yeah.
Okay, thank you.
So oftentimes when this happens, when you form a neutron from an electron and a proton, it also gives off a neutrino. Okay. You guys remember what a neutrino is? It was a fundamental particle in the Standard Model. But of course, so was the electron, right? The proton was not a fundamental, it's a hadron. Neutron is not a fundamental particle, it's also a hadron.
Yeah, I was actually going to ask you to talk about a neutrino again.
Yeah, I mean, they're just, you have neutrinos and you have antineutrinos, which would be the antimatter portion, right? So electrons and neutrinos are some of the fundamental particles in the subatomic particle model of matter, known as the Standard Model. So they have very little or negligible mass and no charge.
So neutrons, protons, and electrons aren't considered fundamental?
No, because you can break them down,
Oh, I see.
right? Yep.
So a neutrino and electron are both of the fundamental units?
Yep, they're fundamental particles. You can't break them further down.
I see.
Yeah. So anyway, here's a couple more examples. And then we have fusion. So fusion happens when smaller nuclei are fused together into a larger nucleus. This is not spontaneous. You cannot use the half-life. So let's think about this. Here's two hydrogen atoms. This is one neutron. This has two neutrons, right? So we force them together and they combine to form helium and give off neutron radiation. Now, what would it take to take these two elements and push them together? If you take two hydrogen atoms and you just put them together and they form a bond, that's hydrogen, H2. That's a chemical reaction. So to get past that, you have to take the electron clouds and push them past each other and make it so that the two nuclei come into contact and share the same space. That requires a tremendous amount of force. You can't like just take two hydrogen atoms and like put them on top of each other and hit it with a hammer and expect that to happen. But when it does, you get a lot of energy. So this is the nuclear reaction that happens what's called the hydrogen bomb, which is actually a fusion bomb. So it requires a tremendous amount of technology. It's about 1,000 times the mass, the explosion of an atomic bomb, which is fission. And just to give you an idea of what it takes to make a fission bomb happen. Here's a bullet. So this is rim fire, where the hammer strikes the rim. Here's center fire, where the hammer strikes the center of the casing. In both cases, you have a primer and you have gunpowder. Spam risk coming from New York City. Sorry. So would you be concerned if you walk into the classroom and your professor's taking a bullet and like throwing it all around the classroom? Would you be afraid that that bullet would just like go off and then kill somebody? The answer is, it's most likely not going to go off. You might be a little bit concerned because why is your crazy professor throwing stuff around the room? But you shouldn't be really afraid of the bullet going off because the gunpowder itself is not pressure sensitive. Nowhere near what the primer is. The primer is pressure sensitive. So how do you make the gunpowder go off? Okay, you center the energy on the firing, on the primer. That is pressure sensitive. It causes that to blow up. But that explosion, that little explosion, causes the rest of the gunpowder to explode. So this is the way that a fission bomb works. How do you get a fission bomb to actually start? You have to use a conventional bomb. You have to use that conventional bomb to actually cause an implosion rather than an explosion. How do you make a fusion bomb go off? The primer for the fusion bomb is a fission bomb. But the primer for a fission bomb is a conventional bomb. And obviously, all of these things have to cause an implosion. So you can imagine that the technology to do this is fantastically complex.
I feel like we're not really aware of how complex it is.
Not even.
Yeah. Like I think we really take it for granted. Like some people like invented all this stuff and we don't even think about it.
Yeah. I was reading an article on what it takes to get the mirrors to all put together for the 30-meter telescope. And the mirrors are partially made, and then they're going to be shipped up there. Then they have to be put together. And then it's going to take another couple of years to fuse those pieces of the mirrors together to get a perfect atom by atom continuous mirror that's 30 meters across. Just the technology to produce those mirrors is more than most people can comprehend. So much so that it's kind of unlikely that one country by its own will be able to produce that. Anyway, so fusion has the potential to supply a safe and limitless source of energy. So this is what they think happens in the sun. Protons and electrons are pushed together to form neutrons. Neutrons and protons are pushed together to form helium. So then the helium can then be used to fuse with other isotopes to form larger atoms. Some people think that this can also happen. Right now, we don't really have a way to prove that in any way, but it's this speculation by what we can go by here on our own instruments, and what we can surmise happens in the sun by looking at, telescopes and everything else. So the sun really consists of plasma. So it's really the fourth form of matter. I didn't talk about it because it's really not important here on Earth. So you got solid, liquid, and gas. Every case you're getting higher and higher temperatures, right? If you get a high enough temperature, then the electrons get so much energy that they're not even associated with the nuclei anymore. So you don't really have atoms. You have these electrons flying everywhere, and you have these cations flying everywhere. And that's what's in the sun. So then the last type of chemical reaction, or nuclear reaction, is transmutation. So transmutation occurs when one element turns into another element. And the only way that can happen if it gains or loses protons. And it does that, it becomes a different element. So here's kind of a transmutation. Almost all of these are transmutations. Okay. Uranium turning into neptunium, then plutonium, here into barium. These are all transmutations. Okay. So somewhere in here, there's only one thing that is not a transmutation. Let's see, where did I put, oh, it's way up here. This right here is not a transmutation, is it? Because the number of protons didn't change. So the element didn't change. Not a transmutation. All the rest of them are.
So would that be considered a nuclear reaction, or is that just a chemical reaction?
Nope. A chemical reaction, you cannot change the number of anything in the nucleus, right?
Yeah.
In a chemical reaction, the nucleus stays the same. So you cannot have transmutation.
Yeah, yes. Yeah, that's what I was saying about that one that you were showing earlier. The protons never changed at all, right?
Right, exactly. So it's not a transmutation.
So wait, why is that one considered a nuclear reaction?
Well, because you're messing around with the nucleus. You're using the nucleus. It goes through a rearrangement. So, yeah.
Gotcha.
And it does give off radiation, doesn't it? So anyway, I think there's enough practice there. And the next real skill are half-life calculations. So the half-life is the time it takes for 1/2 of an isotope to decay on its own spontaneously. So that little table on the periodic table lists several of the different half-lives for the different isotopes. One that's on there is carbon-14. So the half-life of carbon-14, I'm going to write it is 5,730 years, plus or minus 40 years. Okay. So notice that I got 3 significant figures. So it's plus or minus 10 right here would be the uncertainty. So plus or minus 10 would be the implied uncertainty. The precision is actually plus or minus 40 years. That's a calculated precision based upon experiments. So it happens to be 4 times greater than the assumed uncertainty. In any case, what that means, if you had 100 grams of carbon-14 in a sealed container, so nothing could happen to it, after 5,730 years, you would have only 50 grams of it left. That's what it means by half-life. So I decided to use carbon-14 because you guys know about carbon-14 dating, right? So carbon-14 dating is like when your parents go on a date. Oh, no, sorry. So we use that to date how old objects are. So most of the carbon on planet Earth is carbon-12. The amount of carbon-14 on Earth is very low. And as it gets older and older, there's less and less of it. So it's more difficult to get the age of older things. So what that really needs, what really needs to be true, is that the Earth has to have the same amount of carbon-14 to carbon-12 now as it did the thousands of years ago, where we're going to try to use carbon-14 to date an object. You understand what I'm getting at? The amount of carbon-14 on planet Earth has to have been stable over the period of time that we're going to use this technique to date objects. So now we kind of need to know, well, where does carbon-14 come from? Here's where it comes from. Nitrogen, in the form of N2 in the atmosphere, gets hit by neutron radiation. So this is neutron capture, right? Is that a spontaneous event? Yes, it is. And then that gets captured, then a proton is given off, and I end up with carbon-14. So that's proton radiation. So that's a spontaneous event. We're not controlling where the neutrons come from, but we would look at that as a bombardment, but we can't control it. It's a natural thing we're looking at. So what this now means is that in order for the carbon-14 to be constant through time, the bombardment of neutrons from the cosmic radiation also has to be stable in time. We have no way of knowing that. However, when we look at the time points that we have available to us now, it does appear that neutron radiation has been constant over the period of time that carbon-14 dating is useful to us. Neutrons are neutral. They are not deflected by the Earth's magnetic field, which we know does fluctuate. Not only that, we compare the dating of carbon-14 of an object with the dating of that same object with other isotopes, and we get excellent correlation. So, here's another thing that you need to understand. The isotopes all have the same electronic structure and they form molecules accordingly. Their chemical properties are not the same, whether it's carbon-12 or whether it's carbon-14. These two molecules will have the same chemical properties. So now here's how it works. When you're alive, your body has the same ratio of carbon-14 in it as does the environment that you live in, because you essentially are eating your environment. You build up your body with atoms from the environment. So you're incorporating carbon-14 into your body, and then when you die, you are no longer bringing carbon into your body. So the amount of carbon-14 in your remains are going to decrease because of the half-life, and the carbon-12 is going to stay about the same. So the older your remains, the lower the ratio of carbon-14 to carbon-12 is. So let's construct a graph showing the mass of carbon-14, how it diminishes over time. And for each half-life that passes, we're going to take the mass of the isotope that we started with and basically cut it in half. So for every half-life that goes by, we simply take the mass and divide by 2. So mathematically, here's what that means. The mass that we have now is equal to the mass that we started with times 1/2, which is the same thing as dividing by 2, right? But how many times do we divide by 2? Well, by the power of n. N is a number of half-lives. So what happens if n is 1? If 1 half-life goes by, I'm taking the mass and dividing by 2. If n is equal to 2, if 2 half-lives go by, I'm dividing by 2, and then I'm dividing by 2 again. Get it? So when you have this type of equation, n could be a fraction. It could be 2.2. It could be 2.9. But we're not going to have to do that in this course. I just want a conceptual, I just want the concept here, not trying to do exponential equations on our calculators. So here's a simple way to do this kind of math. Starting with 100 grams of carbon-14, how much carbon-14 remains after 1 half-life? Okay, I'm multiplying by 1/2 one time, the answer is 50. Here's another way to look at it. You start with 100. After one half-life, you got 50. Now, what happened to the other 50 grams? According to the law of conservation of mass, you just can't have mass disappear like that. What happened to it? Carbon-14 decays spontaneously, according to the half-life, into nitrogen-14 by giving off beta radiation. Okay. So a neutron split into an electron that came flying out and a proton that stayed in the nucleus. So what about two half-lives? Starting with 100 grams of carbon-14, how much remains after two half-lives? Well, one half-life would give you 50. Divide by 2 again, you get 25. That's your answer. Here's the way I do it. I start off with 100 grams. One half-life would give me 50. Another half-life would give me 25. So now I got 25 grams of carbon-14, 75 grams of nitrogen-14. Then I did it for 3 half-lives. Get it? 1, 2, 3 half-lives. Here's 4 half-lives. So then I put all of this information on this graph. Starting with 100 grams of carbon-14, right? At 0 time. What happens after one half-life goes by? Well, that 100 is now 50 over here. Now what happens if another half-life goes by? That 50 gets cut in half to 25. Then that 25 gets cut in half to 12 and a half. That 12 and a half gets cut in half to like 6 1/4. See that? And the curve that we get is called an exponential decay. So here we have 100% carbon-14, 0 nitrogen-14. After one half-life, we got 50 grams of carbon-14 and 50 grams of nitrogen-14. Notice that the total mass stays about the same because of the law of conservation of mass. You get that so far? Now, after many years of teaching this, one day I realized that what we're looking at is really half of a hyperbola. A hyperbola would go like this, then off like this. But this half has no physical meaning, so we ignore it. But what do you know about a hyperbola? A hyperbola asymptotes. It gets closer and closer and closer to the 0 over here, but never reaches it. So that's mathematics. You'll never reach 0. But in reality, at one point, you're going to have one carbon-14 atom left. And when that decays, you're going to be at 0. So it's an interesting contention about math, isn't it? I have mathematician friends. They really want the world to be perfect like mathematics. And then they get upset when the math is not perfect. So I have to tell them that math is not perfect. It's simply a close approximation to reality. Because reality is what I would consider to be perfect. And they don't like that analogy at all. So is this a direct proportion? No.
No.
Did we use conversion factors to calculate it? No, we didn't. We use this. When we do this process, it's the same thing as this. It's an exponential decay. What about when we convert the number of half-lives into years. Is this a direct proportion? The answer is yes. Converting half-lives into years is a direct proportion. It's a straight line passing through the origin. So here's the words that were coming out of my mouth. And then let's just do a couple of problems. So how much carbon-14 remains after so many thousand years if you start with 750 grams? And the second is how much total mass remains after that period of time? And here's the half-life, which is a direct proportion. So what I need to do is find out how many half-lives. So here's the years. I start with years. I want to get rid of years and keep half-lives. So that's a direct proportion. That means that it's 5 half-lives. So what about the exponential decay part of it? We won't use the equation. We'll just use this. So I have to cut 750 in half 5 consecutive times. So once, twice, 3, 4, 5 times. That's our answer. Okay. So how much total mass is there? Still about 750 grams. I'm not going to say I got the same number of significant figures, but it's about the same. I could have lost some mass because it equals mc squared, but most likely not much. How long will it take for 660 grams of carbon-14 to decay into 41.3 grams? So now I got grams and grams. I can use that to figure out how many half-lives went by. So 660 divided by 2, divide by 2, divide by 2, divide by 2. So look, it took 4 half-lives to get from 660 into 41.3. But they're not asking for half-lives, they're asking for years, so I have to do that conversion. 4 half-lives, get rid of half-lives, keep years. That's about 22,900 years. And so these are huge amounts of numbers right here. Here's something that's maybe a little bit more realistic when it comes to radiocarbon dating. A bone fragment should contain 0.1234 grams of carbon-14 if it were alive recently. A mass spectrometer yields only 0.0077 grams of carbon-14. You're supposed to have 0.1234, you only got this much. So you got mass and you got mass. So how many half-lives went by? Okay, divide by 2, divide by 2, divide by 2, divide. Oh, it took me 4 half-lives to get there. So now, how much years is that? 4 half-lives, that many years for half-life gives me about 23,000 years. That bone fragment is about 23,000 years old, plus or minus at least 1,000 years. So the reason why I wrote this problem here is because I want you to realize something. Can a chemist with a mass spectrometer just grab something and then figure out how old it is? The answer is no. Look at this. A bone fragment should contain that many grams of carbon-14. How the heck would you know that? And what do you guys know about bones? The leg bone of a bird is hollow. It's light because it has to fly. The leg bone of, say, a rhinoceros is extremely dense because it has to withhold tremendous amounts of weight, and it doesn't fly. So when you find a bone, you have to have certain knowledge of the biology of that bone. You also have to have certain knowledge of where was that bone found, what other elements are actually in that bone that came from the environment. So dating an object is way more complicated than just taking a sample and putting it into a mass spectrometer. So we can only do about 60,000 years old because carbon-14 is a very small amount of the amount of carbon on Earth, about 1 part in every trillion. So what that means is 1 gram of carbon-14 for every trillion grams of carbon on planet Earth. So if the total mass of carbon in a modern object is 100 grams, so you have an object with 100 grams of carbon in it, there's only 10 to the minus 10th grams of carbon-14 in it. And the older it is, the less carbon-14 there is. See the problem? So how is it that we can even measure such small quantities? Well, we have what's called the accelerator mass spectrometer, which can actually count atoms. So you need only about 20 to 500 milligrams of a sample. So that's up to half a gram of the sample. The sample is destroyed because it's got to go into the gaseous phase. But it's a tremendously small amount of sample. So there was archaeologists that had samples that were extremely rare. And rather than like going out and doing a quick and dirty thing about, let's find out how old this is, and then I can write a book and be famous, they didn't do that. They waited their entire careers for this mass spectrometer to be invented because they cared about the science and the integrity of the data more than their careers. So anyway, we'll stop there, and when we come back on Friday, we'll pick up about here, how radiation is in our lives everywhere. Hopefully not in our bodies. So if you look at this chapter, what are the real skills? Well, first, understanding what radioactivity is, right? Ionizing radiation, how it gets measured and how it causes damage. And then using your periodic table to complete missing things in nuclear reactions. And then the last skill, categorizing them. And the last skill is half-life calculations, which I've tried to make extremely simple using this methodology here. Okay. So does anybody have any questions about today's lecture?
No questions.
What about anything else, even from or related to exam 1? Anything? Well, you can still email me questions about exam 1 and use the discussions tool on Laulima. Okay, so we won't do anything tomorrow. Tomorrow's Kamehameha Day. And I guess I'll just try to see you folks on Friday. Oh, Friday at noon, I have a system meeting again. We're trying to figure out for fall still. So I won't be able to do it at noon, so we'll do it maybe at 1:30 on Friday. Okay, I'll send an email out.
Sounds good.
Okay, great.
Thank you.
Thank you. You guys have a great Kamehameha holiday. Okay. Try not to conquer any islands or kill a bunch of people.
So tomorrow know the exam.
Tomorrow is the exam too. Today and tomorrow.
Today and tomorrow exam.
Yes, for 140 for Biochem 241.
For what? Sorry.
Are you in Biochem or Chem 100?
Camera handshake.
Chem 100. I'll send out an email. I was figuring that out this morning. I think we'll have our exam Monday and Tuesday.
Next Monday and Tuesday.
Yes.
Okay. So we don't need to carry about this recently 2 days for the exam, right?
Well, we still got to cover the material.
Oh yeah. Okay.
Yeah.
So you mean the chemistry, the 100 take the exam on the next Monday or Tuesday, right?
Yes, exactly.
Okay. Thank you.
Okay.
Thank
Okay.
you.
Take
Have a
care,
good day, bye.
folks. See you.
Have a good day.
You
Thank
too.
you.
Take care.